All right. So thanks everyone for joining us today. I hope you all had a great week. Today we have the pleasure to host Hervé, who is an associate professor at Polytechnique Montréal, an associate member of MILA, and he'll share with us some thoughts on spectral geometry of graphs and learning. So before handing the mic to you, Hervé, let me remind you all of some house rules. As usual, clarification question will be allowed to be asked during the talk. For people in person, just raise your hand and wait for me to give you the mic so that people online can hear you. And for people online, you just have to type the word question, I have a question, and when the time is right, I'll let you directly ask it. There'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Hervé. That's pretty much it. Whenever you're ready, floor is yours.
Thank you, Him. Yeah, thanks. First, I wanted to thank you as well. I remember about 5 years ago, and I gave a talk, and the next day was the NeurIT deadline. And I think that there was a room filled with one person, and that was the person inviting me. So that's the lowest I could go. And actually, here we are about not tomorrow, but 2 weeks ago, 2 weeks far from NeurIT. No? So I wanted to thank you for for being here as well. And so I wanted to share a bit some thoughts on work we do in the lab as well on spectral geometry and how this could be used for things we can all do together. Spectral geometry, that's what I like to do, with some examples on brains as well. But before I start, I kind of like to start with a slide on. You may wonder, like, who is this guy in front? So I like to share this to start with this slide. I started maybe about 20 years ago. In a lab where I noticed 2 or 3 people here was in the same lab, Siemens. It was actually a major hub in computer vision. So we were doing that kind of thing. For example, in the heart, you want to segment, image segmentation. You want to register, do the different things on the heart. And then you want to play around and then plan surgeries, for example, measure things like vessels or things like that. So that was the thing we were doing then. And back then as well, in the computer vision conferences, the major thing, it was even called the graph cuts conferences. So the graph cut paper was super nice on papers, but if you want to actually play around with this, you needed like a lot of RAM, not even GPU nowadays. But so it was basically nice on papers, but if you want to play this on medical images, which is like gigabytes of, remember 20 years ago. So we did some multi-level aspects. So because of this work, actually it's still up to today, is my most cited paper. So you see how things can go sometimes. But that was actually fun work to do as well. Because of that, graph cuts as well could be used on many type of papers. So it's still one work that I'm kind of proud of as well. Any hospital I go, I kind of notice the machines that has lines of code that I did on those machines. So it's, I don't know, some pride when I visit around. But still, back then I was mostly an engineer or an intern. I started, and then you feel like everyone around me has a PhD. So what is this PhD? I want to do a PhD as well. And so I continued. mostly on still working on image segmentation, some registration as well, but on graph-based approaches. Then a PhD is never enough. Once you're hooked, you stay. So I did a postdoc as well with McGill here. Kalim was my mentor when I was at the years of McGill here. How do you actually measures not only on pixels, but on orientation? Every pixel has an orientation. It's a whole matrix. And it's as well a matrix that has particular properties, a symmetric positive matrix as well. So there's a lot of fun math to do around here. And a lot of geometries are starting to appear here as well. A manifold, how do you actually enforce the matrix to be still enforced as a positive symmetric matrix, for example. Finding matching correspondences between meshes as well. If you, for example, point on a mesh, a point on my brain, what would be the equivalent point on somebody else's brain as well? So in neuroscience, it's really funny to see how there's a discrepancy between methods, super cool method we find on papers, and what's used on the field. To find correspondences across a whole brain, it takes like hours and hours and hours, about 20 hours, maybe a bit faster now. With those approaches, it's a matter of even less than a second. So it's actually fun to play around with this. And then I got a faculty position back in France as well. And more and more onto the understanding how manifolds, the curvature, the shapes of those manifolds. If you actually ignore this, in this particular field of medical images, the major constraint is you don't have millions of images like in computer vision. So enforcing or leveraging anything you can do, and particularly manifolds, if you have a data set, every image is a point on this manifold. If you actually leverage this information on the geometry that you have there, there's a lot of things you can do. This is fun to explore as well. So that's what we do in the lab. And then I decided to come back here in Montreal. So I was on the other side of the mountain here. And recently, since January, I moved. I changed things you should not or should do sometimes. But and so that's basically a bit wondering who is this guy in front. So that's basically what I wanted to share. Then you see as well in a career. I mean, it's nice to move around, explore, having different opportunities as well, like learning more and more as well. And in the team, we explored a few themes, mostly around how do we exploit complex geometries. Like the brain is highly folded. There's a lot of opportunities in there as well. How do you do a convolution on a super folded manifold, for example, or a convolution on a same thing? Imagine a manifold in high dimensions. How do you do all this as well? My approach, I like graphs. So there's a nice things to do on graphs as well. How do you do statistics on something that is highly curved as well? For example, you have signals on the brain. How do you do a simple thing as an average? What is the standard deviation on something that is highly folded as well? Imagine this in 3D, but in high dimensions as well. Same methodologies here. Fast correspondences as well. Spectral matching. I'll tell a bit in this talk here. Yeah, how do you do learning then? How do you apply those, for example, deep learning, but on something highly folded or on a graph in general as well? Understanding the variability of different shapes. In the anatomy, I find it super fun because shapes doesn't happen randomly. A heart always have kind of 4 chambers, for example. It has a particular type of geometry. So how do you explore these things that you can find? Again, because shapes are not necessarily random in an anatomy. That's something you can leverage to compensate for the lack of annotations in particular. And it's fun to see as well in the computer vision community, the semi-supervised, unsupervised, all of this is catching up as well. But we don't necessarily only do computer vision or algorithms as well, but visualization. Once you have fun segmentations, fun imaging that you have, you want to explore around things inside as well. So this is another thing that is a bit more difficult from my view, but to publish. But it's something I really enjoy doing as well. We don't necessarily only do medical imaging, but it's to debug or develop algorithm as well. It's fun to test on any type of shapes. For example, those funny animals running around. And yeah, so that's basically what we covering roughly what we do in the team. So that was a bit for the introduction. And I like to describe myself as a shape person, a shape guy. How do you exploit meshes? How do you exploit meshes, but in high dimensions, for example, that becomes a manifold, but it's all about the same ideas that you have here. How do you find correspondences, for example? Imagine instead of points, but you could have a distribution. Oh, yeah, there's new people coming, yeah, correspondences. If you have the shape, for example, of a brane, which is highly folded, how do you exploit those geometries? So this is in neuroscience, it's fun because I mean we all have a brain and we function with the brain. So understanding the brain is actually fun too. That's something I really enjoy as well. Whenever you find something cool, you find exciting, you go talk with a neuroscientist, and the answer is often, oh, cool. That's what we don't know how it works. So that's fun as well. Yeah, so that's on the brain that you have here, but same type of tasks or problems that you have to face. How do you segment? How do you classify things, for example? A particular brain, is this Alzheimer's, not Alzheimer's, for example? You want to do a regression. What is the age of this simply by looking at the shape of the brain, for example? You may wonder why learn on surfaces. Well, surfaces, again, if you want to do statistics or learn something on a brain, on a highly folded surface in particular, well, in the neuroscience field, there's a lot of information or data that fundamentally lives on surfaces. The points are not necessarily random, but they live on the surface. And an interesting thing as well, the brain itself, most of the neurons or the body of the neurons lie on the very thin surface of the brain. Inside is mostly cable connecting those cells, those body of the cells. And so that's one of the reasons as well as something we don't necessarily understand as well, but it's why the surface is highly folded, so that maximizes the surface, maximizes the number of body cells as well. But because of this highly folds, high folding, it's creates a lot of complexity as well. And mostly in neuroimaging, if you have those complex, huge machines, fMRI, MRI, things like that, they measure things volumetrically. That means you measure a voxel and intensity on a measure on a voxel, a 3D grid. However, I mean, it's a surface, so you using maybe something, there's something strange that happens here. I'll show you why. But this is more or less the context of what we do here. As I was mentioning, if you want to do purely computer vision approaches and so on, this is great. You have a tool that we often take for granted. We have a grid. So that means you exactly know where is your neighbors. You exactly know your neighborhood structures. You know where is your left, your right, your up and down, for example. You simply, for example, increment an index in when you code, plus I, plus 1, plus 2, and I or J or K. So this is great because then you can apply things like a convolution. You know how to navigate things like that. But on a brain, on a highly folded surface, on a mesh in general, what is the up and down, left and right, if you are yourself on a surface like the highly folded surface of the brain? Even worse, I mean, if you start to walk, for example, on the surface of a brain, you can even find yourself upside down because it's highly folded. Like the notion of up and down is all a bit crooked. So it creates a lot of complexity here. Something that is heavily used, or you rely on images, grids, you exactly know where are your neighbors. While on the surface of the brain, again, you can find yourself upside down. It's a bit tricky to apply as is the computer vision methods that you often have. Even worse than that, if you look closely, take, for example, two neighboring points on the image here. So two voxels or two pixels that are neighboring each other, they're really next to each other. So if you completely ignore the geometry, well, fine, but the regularization, when we have the regularization of your methodology, those will be more or less taken for account that they are neighbors. But in fact, they could be very far apart on the surface because it's highly folded. So that means on the surface, those points can be highly, highly different. So that means the regularization would create there's a lot of confusion going on here. And that creates a lot of problem if you apply convolutions, for example, as is convolution-based approaches on images. If you ignore that you're dealing with a highly folded surface, this will be a bit problematic here. So on an image, on a 2D image, doing a CNN or convolution, that's fine. You know exactly where are your neighbors. You simply increment an index and you're done. However, if you want to do a convolution on a highly folded surface, well, then things get tricky. Why not to do even a PhD or? But this is actually fun problems that leverages. You need to take into account how to model a geometrical shape that is this. Another thing we often take for granted as well is in these CNN approaches, for example, you have the convolution layers, but you also have the pooling layers. Again, if you heavily rely on the notion of the grid that you have, That's great, but how do you do a pooling? I mean, for example, an average or a max pooling, things like that. But on a graph, I mean, what is your left, your right, your up and down? I mean, even the neighborhood structure is not even regular, for example. So the pooling system is not necessarily as trivial as well. So that's you see a bit. There's some challenges to face here. So moving from image to something that is highly folded or highly complex. That's enough to have some fun there. So this is great. So I wanted to share, depending on the timing, but I wanted to share a bit how to play around on convolutions, and if we have time, maybe how to play around with pooling as well. But before that, so all of this since about a few years already, but it's highly related as well to a parallel track of a body of work as well, and geometric deep learning as well. So some background, maybe some background for those who are still not familiar with the concept here. If you have an image, fine, you can do a convolution, no issue here. Convolution is simply a filter that you scan. Maybe I shouldn't spend too much time on this, but it's simply like it's a window that you scan, and the goal is to learn what is the value of those filters that you have in this small window that you have here. And then you can even cascade. You build the architecture that you want, and so on. You can mix a bit using a regular network in the end. But the whole secret here, not secret, but the whole core that you have here, you rely on this convolution that you have here. So on an image, that's fine. But how do you do this on a graph? So that's the thing that I wanted to share here. If you remember your calculus classes, just a few years ago, even myself, calculus was, but yeah, you have a convolution. If you remember, a convolution in our space, in the Euclidean world, in the Euclidean space, Euclidean domain, a convolution in our world is equivalent to a multiplication in a Fourier space. You just change your space, your domain. So the convolution becomes a multiplication. A multiplication is easier to play around, especially with GPUs, and so it's easier to work with. And this is not a novel idea, it comes from even Fourier, 1822. But great, but still, like, what does it have to do? How do you do this on a graph, for example? But just remembering that, yes, a convolution in a Euclidean world is the equivalent of of multiplication in the Fourier space here. So in the earlier work of the geometric deep learning body of work, this is how things are relied on. So you move to the Fourier space, and then you multiply, and then you come back on the inverse Fourier that you have here. That we can write in the form of a matrix, and the matrix form as well. So F is your image, for example. G is your filters that you have. I don't necessarily like to show mathematics. This is the only slide with mathematics that you have. And but the goal here is to learn what is the value of the filters that you have. Your G that you have, the blue guy here, and you want to learn what is the value that you have here. Since those are regular values, you can, as any signal, you can write this as a function, as a combination of different bases. You have different coefficients to learn. And from this, you can reconstruct or guess what are the values that you have in this filter here. So the way it was done in the earlier body of work was using the Chebyshev polynomials. It's classical tools to play with the signal processing, for example. So now, instead of learning all the values that you have in your filters, you simply learn the coefficients of this polynomial here. The theta that you have here, that's what you want to learn now. So you have much less values to learn, so that's great. So what you have to learn here, again, is this combinations of summation of theta's that you have here. In the earlier work as well, instead of having multiple degrees of the polynomials, you say, oh, let's only do the first order approximation that you have here, theta 0 and theta 1 here. So this is great. And then 2 parameter was too much, so let's make them equal. Let's learn 1 theta. So that was actually enough to learn a lot of things in the problems that you had here. When you think intuitively what's happening here, in fact, what you're learning is basically a diffusion. You learn a diffusion on a graph that you have here. And by learning the degree or how much spread you have on this diffusion, it's actually a super powerful tool to learn a lot of things on graphs that you have here. So that was the inner core of the earlier body of work that you have here. So this convolution I was mentioning here, in the Euclidean world, becomes simply a multiplication in this Fourier space here. And what you have to learn now is simply this theta parameter that you have here. You can have multiple degrees, or simply a first order approximations, or one theta that you have here. So in terms of learning pipelines and so on, that's super great, because this convolution that you have here now becomes a multiplication here. And what you need to learn, again, is this single theta parameter that you have here. So doing a convolution on a graph was simply a matter of, you have your inputs, the input layer. Those are the blue guy that you have here. So that those are the values that you have on the nodes of your graphs. You multiply, those are, for example, the weights that you have in your graph here. So this is what you need to learn. So this becomes a simple multiplication here. And then you have your output. And also, once you have that, you can actually even cascade the whole pipeline. That was mostly the inner ideas that you have here. But still, you may wonder, like, okay, what is this thing with one single parameter, one theta? It's maybe not enough. It's not necessarily fun. No? So, but one trick was to actually, okay, let's have multiple thetas, multiple channels, for example, and then you can actually leverage a lot of things behind that. But still, if you want to have some kind of more fun or richer kernels, and that's another body of work. Or instead, you learn still a bit like a convolution filters, more classical on an image. But if you have a small plane that you have, for example, on your mesh here, imagine you have a bit like a diploma hat, for example, your mortar hat. And then you have your, you can parameterize once you have your diploma hat, the square hat that you have. Well, once you have your square, then you can actually have some kind of a filter, and then you learn what is the value on those boxes that you have here. So that's what you want to learn, ideally. So you have the whole pipeline to learn those values here. But once you have this parameterization, you have your mortar hat that you can actually move around on your mesh. That's great. And then you can build all your fancy architecture that you want. But the goal is to learn the values of those bins that you have on your mortar hat here. So that created a whole body of work as well, mostly from colleagues from London or Switzerland as well. But still, how you parameterize this mortar hat? If you have a polar coordinate, your seal core, you have your angle, the theta, you have the distance that you have that you want to do. But still, for example, if you have, again, the coordinate axis, how do you place the axis? What is the angle 0? What is the definition of an angle 0? So that is fine if you, for example, it's always going to be the up vector, but you're going to have one problem if you have exactly your mortar hat exactly on top of your head. The angle 0 is a bit undefined, for example. There's a lot of things that you need to think of, which becomes a bit heuristic and a bit nasty. But in the literature, that was possible to do. Different ways to parameterize as well those kernels. You can have regular Gaussians that you want. You can have different type of ellipsoid, different shapes, anisotropic. You can have a combinations of Gaussians, for example, mixtures of Gaussian. Why not? So this particular work that I'm mentioning here is one work that was trying to unify all the graph GNNs that you have all around here. This is not my work. I'm simply showing what's going on the geometric deep learning aspect here. But again, the whole goal here is to learn those weights that you have, and the weights are the parameters that you have of those small Gaussians that you have here. The nasty part was you need to actually compute how do you place your mortar hat, your diploma hat. How do you find this orientation of this angle 0? So there's some heuristic going on here. In the literature, mostly was the angles of minimal curvature, for example, or maximal curvatures in that case. But still, why not? But then there's another body of work that I kind of like is the spectral shape analysis, and this is where things start to be fun a bit. If you have so it's actually a cool video. This guy likes to vibrate a lot of things, including water, fire. He goes to space, and then there's music associated. I'm not playing the music here, but it's a cool DJ as well. And so he likes to vibrate a bunch of things. But if you have a plate, just a regular square, for example, like here, different frequencies, it will form different shapes that you have, different patterns that you have. And the shape of those patterns are completely, entirely governed by the shape of the vibrating plate that you have here. A square is well known, Bessel's equations and so on. But this can be extrapolated to any type of shapes. For example, if you have the shape of a violin, it's also used to measure the quality, the purity of a sound, for example, things like that. But this is the shape that you have of the vibrations is entirely governed by the shape that you have here. So different frequencies, different shapes. For example, if you have a shape of a violin or a guitar, for example, here, different frequencies, different shapes, those sand here would form different types of lines that you have here. And this is entirely governed by the shape. If you slightly deform the shape, as long as there's certain properties, isometry is preserved, for example, those vibrating pattern would be exactly the same. So this is a very strong properties to manipulate shapes that you have here. And any shape can vibrate, so why not about our horse that we have here? What I wanted to bring your attention, so the color here is the amplitude of those vibrations that you have here. So blue and red is the extremas. This is where, for example, on the left column that you have the coarsest vibration, the coarsest harmonic vibration. That's legs, the bottom and the head, for example, would be the most vibrating aspect here. The further you go in the frequencies, the more complex pattern you start to see here. But what I want to bring your focus on is if you take one same point, for example, the front left leg, for example, if you look at the vibration characteristics or the vibration amplitude, this exact same point would have exactly the same amplitude characteristics here. And this is a property of those spectral coordinates, spectral geometry that you have here. This point here doesn't vibrate a lot in this particular harmonic here. It would vibrate a lot in the second one, a bit less in the third one, and so on. So these characteristics, this point here that you have in space, no matter how you move, it would always vibrate the same. So that's actually kind of cool. If you work in the Euclidean space, if you work, for example, this point has an XYZ coordinate. If, for example, the horse is galloping here, this XYZ coordinate, the value of XYZ would move a lot. So if you want to play on something that is highly moving or changing, it's a bit difficult. However, if you look at the vibration properties, the amplitude that you have here, this one, no matter how much, what are the value of the XYZs, no matter how you move around, those points would be vibrating exactly the same here. So that's a strong properties to find matching, for example, here. And what I want to bring your attention on as well, those horses, if you gallop here, the vibration that you have, the characteristics, even though XYZ values changes a lot, those points actually, the XYZ would, so it's a bit complex to work with things that varies a lot. However, the vibration characteristics is super robust, super stable in that case. So horses are fun. What about the brain? So that's we can do this. I'm not sparing much details, but if you build a graph, you have two neighboring points on the neighboring voxels, or two neighboring, not voxels, but graph nodes, for example. There's a particular distance that you have. I'm simplifying a lot here, but it's more or less the same idea. Those 2 points, they have a distance, and they report node I, node J. You report in a big matrix, row, column, IJ, and then you put your distance there. I'm simplifying, but it's more or less the same idea. You build a matrix like this. So every pairs of nodes gets a point, gets a value in a matrix here. You decompose this matrix, you compute the eigenvectors, and the values of those eigenvectors gives you exactly the amplitude that you have here. So this is coming from the spectral geometry, spectral graph theory that you have here. So this is super nice properties. Again, so those are the coarsest vibrations. Eigenvalues are actually equivalent to the harmonic frequencies. The eigenvalue gives you the amplitude. And if you look closely, this is a property that comes from as well those spectral graph theory as well. So the coarsest harmonics, same thing. It would vibrate from the longest axis of symmetry, for example. I'm simplifying again here, but it's it would vibrate from top to bottom of your heart. Second harmonic would vibrate differently, and the more higher frequency you go, the more complex patterns that you have here. Another aspect to visualize as well, instead of plotting your mesh using X, Y, Z, those are the brains that you would get, the regular Euclidean world. But if you look closely, those are actually axes that fundamentally lives on the surface here. Those are smooth monotonic values that increase on your mesh or on your graph. And by having those values by exploiting every point, not using their X, Y, Z values, but taking those values in the spectral, I call this a spectral domain, for example. Instead of plotting those meshes, you're using your favorite tools. instead of plotting them using the XYZ values, you replace XYZ by the coordinate of those spectral amplitude that you have here. And the shape that you have would be those kind of shapes that you have here. So this complex brain, two different brains, if you overlap them, the folding are never really overlapping. It's a bit too much complex. Not complex, but it's like you have a bunch of difficulties that exist in the Euclidean world. You simply plot them, replace XYZ by UVW, for example. Those would be the spectral amplitude. Those would be the shapes that you have here, those blobbish shape that you have. So now you start to see, okay, those meshes that were highly complex in the Euclidean domain, those vibration characteristics, there's something going on here. It's much easier to just visualize, and if you want to find a matching in there, that's actually getting fun here. And actually, to find matching, you simply overlap those points, those meshes. You simply refine a little bit, but then simply the closest point, the nearest neighbors, a simple algorithm, nearest neighbors, actually find you super fast way to find matching correspondences across brains that you have. And that makes a difference. For example, in the neuroscience field, there's a lot of tools. Takes a bunch of hours to compute, for example, all the correspondence that you have here. But by using these spectral correspondences ideas, that's less than a second nowadays. This is actually an old slide that I came from my own PhD. I think Chris here and Kalim as well, where it's actually funny. There's two jury of my member, my PhD here. But yeah, so that was fun. All I want you to remember here is these axes that you have here. And those axes, UVW, those spectral amplitude I was mentioning, those axes are actually fun because they fundamentally live on the surface. They fundamentally they are fundamentally tied to the shape that you have. It's entirely governed by the shape that is vibrating here. And if you have a brain here, well, this UVW, not XYZ anymore, but this UVW, they're actually all wrapping around. They're guaranteed to be on the surface that you have here. Instead of using or relying on an XYZ or an image on a XY, for example, those actually arbitrary choice. No, it can be XYZ like this, can be, you can rotate it anyways. And the way you rotate, it would completely change the values in for example, when you learn. So you need to somehow flip it up or flip. So this is a bit of an arbitrary choice in that case. So that's great, but what does it have to do with machine learning? But what I wanted you to remember is this spectral axis that we have here. So this is great. Back on computer vision, convolution, well-defined, because you have this grid. You exactly know where are your neighbors. That's great. But now we made a small detour. I just give you a super nice tool, which is to play around with this spectral axis that you have here. And because of that, you simply now increment an index, not in the Euclidean space, but in the Euclidean world here. So now you have, this is a simple math, back then it was MATLAB, but it's simply a convolution, a Gaussian that I put on the mesh, highly folded. I simply incremented this +1 on one of those spectral axes. And then you can have this convolution that actually is guaranteed to live on your surface that you have here. Again, on the brain here, you build a graph. Every tiny small pairs of points gets a distance. You report node I, node j a distance. Row, column ij, you put the distance in your matrix. You compute the eigenvectors, eigenvalues. That gives you the axis that I was mentioning here. And this is a multi-dimensional world as well. And because of that, then you have all the regular tools. You simply replace the XYZ with those eigenvalues that you have here. So, for example, on a grid, on an image, that's fine. But on a graph, you simply take those XYZs. So it's mostly in the indices that you increment, but it's the same idea. You take those XYZs, and then you replace with the values that you have here. So it's replacing those with the core spectral coordinates that you have here. So the notion of distance that you have simply becomes a distance, but in the spectral domain here. And behind, I'm not showing this, but behind as well, there's a lot of nice things that comes with the regularization. You're using the Laplacian, so there's a lot of nice things going on as well. But practically, in practice, it's simply replacing XYZ by UVW, the spectral coordinate axis. It may sound like a very simple tool, simple trick, but fundamentally what's happening, you're guaranteed, or you're actually moving to fundamentally be forcing the learning to happen directly on the surface or the graph that you have here. So once you have this trick, then you can build the architecture that you want here. So for example, your regular pipeline, you can do this regular architecture that you have here. But the goal here is to learn again now, exactly like a CNN that you have in an image. You want to learn different filters, Gaussian, things like that, like what is the width and so on. But what's fundamentally happening here is you're forcing the learning to happen directly on the surface that you have. So I should give credit to the right persons as well. So this was a student in our lab, co-supervised by Christian here as well. If you look around as well, how things evolve, different layers, for example, you see what's happening. It's fun to see as well how things are forming, not on an image, but on the graph itself. So that's one of the simplest architecture you could have. But if you want to learn a segmentation, where is the area of the vision, for example, or the BRCA area or something like that, you'll simply learn, and then you see slowly towards the end of the latter stage of your architecture, you see the pattern is actually forming the segmentation map that you want to have here. So different here, a bit on the back, usually the vision, some part in the front here, and so on. To learn as well, you use, it's highly flexible. It's exactly like a regular architecture that you want to have. Cross entropy, you use the favorite loss function that you want to do. But again, the role here is to learn exactly as in a CNN, for example, is to learn simply the parameters that you want to have. In terms of results, those are tables, and what I want to show is if you want to apply as is purely a graph or a GNN, or not necessarily a GNN, but any type of approaches that rely on Euclidean coordinates. GC would be graph convolutions. For example, if you completely ignore the geometry, you stay in this Euclidean world, you use these XYZ coordinates. This is fun. It's a lot of, can be used in many approaches, but in a highly complex surface like the brain, you get results like 50%. 50% is not necessarily good. However, by doing the little trick, by changing this XYZ and forcing learning to happen directly on the surface, this 50% becomes 80-ish%, which is much nicer here, with a very simple trick in a way. And to compare with what's happening in the neuroscience, it's more or less in the same ballpark. I'm not arguing 84, 86. To me, it's all the same thing. But the major the difference is this guy takes a bunch of hours. This guy takes less than a second. So that's a nice thing to do as well. Of course, yeah. Oh, there's a microphone as well.
Thank you. No, my question is related to nowadays there is a fast surfer. So how it compares to this? Because fast surfer is 1 second as fast as this one.
Yeah, and fast surfer we have one of the So those are colleagues of mine as well. But yeah, so it's exactly the same idea. It's exactly the same, and I would put fast surfer exactly on this body of work as well.
Yep. So I guess my next question will be, is it possible with the method that you're showing to kind of be end-to-end in whatever task we want to analyze the brain? Because with FreeSurfer, for instance, we perform the pre-processing, we extract the vertices, and then we build the kernel, and then we do deep learning, machine learning, whatever. Is it possible instead to kind of sidestep these two-step approach and be end-to-end during the
what I'm providing
phase?
here is simply the tool of simply the concept. If there's one message to learn from this whole talk here is not necessarily playing around in the Euclidean world, but in the spectral world. You can apply this. That means you can learn things on the surface. Fast surfer would be falling into this same body of work as well. But what you're talking is a bit different. Like you want to, from the image, the MRI, you want the whole end-to-end all the way to the map that you have here. I'm not mentioning this, but we are relying on, we're using the same approaches as well, same ideas on the spectrum. So for example, from an image, how do you reconstruct the surface? So that we tackle this approach in the team as well. But that would be not this approach. But from the image, how do you build the surface or the graph? From the image, you want to learn the graph structure. So that is possible as well, but I'm not mentioning this, but it's relying a bit on similar concepts. The spectral,
I don't know if I'm anticipating, the next slide possibly, but is there any tool already that you built and make a
Yeah, if you want to reuse those tools, yeah, we
Just
have
to test,
GitHub and GitHub and all to test. There's always the nasty thing of having clean code and all, but it's
all right.
and
Thank you.
and visually as well. Maybe, but that could have answered the question as well. Visually, if you have the ground truth that looks like this, so just to go somewhere else than deep learning as well, forests as well. That's another. So that's a much older work. But same concept, much older than fast-first surfer, for example. But it's you remember those two pixels that are neighbors are close to each other on a brain, but very far apart on the surface. This regularity issue that you have here, that creates exactly the type of problems that you have here. I call these islands regularization problems. You have a lot of small pockets of confusion of regularization because 2 points. The algorithm, if you completely ignore this geometry, 2 points think they are close to each other, but they're super far apart. So you start to have a lot of neighboring structure that doesn't make sense on the surface, but they do make sense on the volume here. Those surfaces have been flattened a little bit, so then we can see what's going on in the whole folder. But if you move this to the spectral world, simply changing the XYZ by those vibration characteristics, XYZ to UVW, this simple move brings you this visual advantage that you have here. So all these regularity issues are completely gone because they don't exist anymore in this spectral coordinate here. So that creates this much nicer and smoother brains that you have here. That's another approach. You're relying the same thing. Here, if you use as is straight out of the box the graph convolution approaches on the Euclidean by completely ignoring the geometry, that's what you have here. It's much cleaner, but you still have this regularity issue that you have here. But if you move this to the spectral world, those regularity are mostly gone here. And then you can massage a little bit, or you can even clean a little bit with some MRS, for example, or some. So that cleans a little bit even better. Just visually to publish, it's nicer sometimes. But the results are more or less, you see, for example, going from the Euclidean world, XYZs, you manipulate those XYZs, get this 40, 50-ish%. The goal is not to compare your forests with SVMs or with the deep learning and so on, but it's to compare Euclidean versus geometric spectral domains here. So from the 50s, you go to the regular, what you expect to have in the 80s. So that's and the main advantage that you gain in using, for example, FreeSurfer that you were mentioning. FreeSurfer takes a bunch of hours. A bunch can be even 20-ish hours if you have a regular computer. But if by using or relying on those spectral approaches, that's seconds instead. Time I'm advancing a little bit. So I covered here mostly what's going on a convolution. I can go fast maybe, but I wanted to cover a little bit fast as well on the pooling layers. You have the convolution layers. That's great. But the pooling layer is often a bit, not necessarily ignored, but taken for granted as well. You simply aggregate, you do an average, or you do a max, and then you get your max pooling. But how do you do this on a graph? That's a bit tricky. But you rely on the same exact tools that you have here. Because everything I was mentioning, or in the literature as well, it's nice you have a graph. You have n nodes, a volume of a graph of n nodes, for example. It's okay to go, for example, from a node to one value that you have here. You want to regress, for example, the age, or find what is the gender or the sex of this person, for example. So n to 1 is okay. So that's great. But you want to have maybe something richer than n to 1, for example. You maybe want to have n to a different n, for example. So that gets tricky because you have a graph. The structure of the graph is not necessarily easy. But there's different approaches. One of them is you want to cluster, for example, the nodes that you have, and then you build a particular cluster of nodes, and then you can do your max or your average pooling that you have here. One good work, actually, that is from one student of Kalim's here as well. If I'm not mistaken, this is this work. Another approach as well, another strategy is to somehow learn this association that you have. You have a bunch of nodes. Depending on what you want to learn, maybe there's something that would be formed or learned this structure that you have here. So that's another approach to do here. On one way, you have fixed clusters, fixed strategy to cluster. For example, fixed number of clusters, for example. Or the other one, you want to learn pattern, but you don't necessarily know where you are on your brain, for example. So you have a bit this localization on your brain that is a bit tricky here. There's you never bread and butter, or you're always something that you have to sacrifice. But from the first half of the earlier slides, I gave you a super nice tool, which is to actually have a coordinate axis that lives on this surface that you have here. So you actually exactly know if you are on the back, in the front, you know where you are on the surface here, and then you exactly know as well how to navigate on the surface that you have. So in our team, we decided to build an architecture on using two different branches. One would somehow learn the assignment or learn this cluster, like how to aggregate the nodes, for example, on one branch. The other branch, okay, once we have that, we want to learn what is the values of the nodes, the new nodes that we have here. You combine those together, and then you end up with the input of a graph of n layers, n nodes. The output can have a new set of clusters and nodes as well. So from n to a different n here. You learn how to assign the different clusters, and then you learn the nodes the value of the nodes that you have here. Graphically, that's how it looks like. You have points. You want to learn, okay, how are the points? How should they connect together? For example, how should they aggregate? If you want to pool, if you want to max them together, which nodes would you work on? So you built in different clusters like this, and then you have you know that you have the new nodes from this graph here, from the 3 points that you have. Now you have one node that aggregates those 3 nodes that you have here. So you have a value on the new nodes. You know how to assign this new value. You assign the new neighbors as well. So you can do this for a bunch of different clusters. So you have your new graph here. So now you only have the nodes. Now you need to connect the points together as well. And this is the value on the edges would be the average values that connects those to the different areas that you have here. So you have new nodes, you have new edges values. So you have everything to build a graph here. And that's in terms of pipeline, or you have your new nodes, the values of the edges. You can build your new graph from n nodes here to a new set of new number of nodes that you have here. And once you have these building blocks, like a bit like a Lego, you can even cascade different ends. You can do, if you want to have something like that encodes the values, for example. You can even decode them. You can build a fancy architecture that you want. You know how to do to assign n to a different n, the new nodes and new edges that you have here. And to learn, once at the very end, you decide the task that you want to do, either, for example, disease classification or age regression. You really have fun the way you want. Same thing. If you want to learn the loss function, depending on the application that you have, cross entropy or whatever. The little trick here, I'm not mentioning this as well, but you have the Laplacian matrix that happens internally as well. So this is a super nice tool to regularize a bit the optimization that you have here. And this trick of regularizing a little bit with the Laplacian that comes from the graph, that helps some stability issues that was a bit nasty in some convolution work as well. Graph work, sorry. Yeah, to experiment different data sets, brains again. What I want to bring your attention, not overwhelming you with a lot of numbers, but it's if you use the strategy of having fixed number of clusters, for example, k-means, you cluster things together, you get, in this particular case of a sex classification, you have about 64% of the data set is correctly sex classified, for example. That's great. Spectral clustering, that was the strategy. Fixed parcellation means you take your anatomical parcellations, you take the visual, so your clusters are fixed. So that's how you apply this. But basically, what I wanted to bring the attention is simply different strategies to cluster, which has nothing to do with the spectral domain. And if you move this to the spectral domain by having this spectral aggregation here, from the 60s, you move to the 80s, which is more or less what you should expect. So that's a geometry-based pooling, we can call it this way here. So I've covered convolutions. So you have your convolution layers. I covered quickly, but I covered the pooling layers. So now you have all the tools to play around. You have convolution, pooling, you build the architecture that you want here. Yeah. So yeah, good. I'm not too late. So yeah, a lot of things are going on. But if you have one thing to remember, the talk I made a small detour on spectral parameterization or the spectral world. These forces that move around, or how do you characterize shapes on spectral domain? Fun things are happening there, and a lot of simplification happens too. One of them is playing around with convolution in much direct way. You force the learning to happen directly on the surface or on the manifold or the graph that you want. Pooling, same thing. And I should acknowledge the right persons as well. Kartik was a student in our team. Christian is here in the room as well. I love to co-supervise students, because you really enrich the fun, the learning, it's only advantage on that. If you want to have some papers as well, there's new papers that I should update those slides as well, but there's reconstruction work that I was mentioning from the volume. How do you reconstruct the surface? So that is possible to do as well. But one thing, if you want to remember, one thing is if you want to play around with the graphs, maybe have a look at what's happening in the Fourier or the spectral domain, for example. Fun things are happening, a lot of simplification are happening. So one thing to remember, one sentence, if you're working with graphs, have a look what's going on in the spectral domain. That's a lot of things are happening there. Then you can read, there's a lot of body of work. Here's a few, but there's a lot of different teams on different approaches here. But the whole concept, if you think in terms of vibration, or if you think in terms of Fourier space, there's a lot of things become simpler in the way you design your math behind. Intuitively, you directly force the learning to happen on something that fundamentally lives on the geometry that you're working on. Limitation, I must emphasize on this as well. If you're comparing graphs, the graphs should have similarities as well. So that means you shouldn't compare apples and oranges, where you have a graph of a particular structure and a graph which is completely funky, different shape, or different, not shape, but topology. If you have holes, for example, if you have the horse is a tough leg, for example, or a brain has a tumor inside, or geometrically, if you're not comparing the same thing, then you should definitely not apply those things, or differently. But those are important things to mention, of course. This as well. Now you need to acknowledge the money behind. That's yeah. I'm sorry for being a bit late, but yeah.
We have time for a few questions or comments, discussion, if there are some. Gonna check online.
All right. Thanks, Hervé. Although I saw this presentation before, it's more a comment regarding the question that was asked. I think Hervé mentioned it at the very end, but there was a work that came after this where this very same student tried to do, because all these works required to have extracted the surface beforehand. But in a subsequent work, there was with a single neural network, was doing the surface extraction plus parcellation, end to end, basically, as you asked.
Oh, yeah.
I have this question related to brain with diseases. For instance, let's imagine not tumor, but multiple sclerosis, for instance.
Okay.
So we have these lesions.
Oh,
right.
That happens to me all the time.
I mentioned something,
wall,
right? When we analyze the surface, usually we analyze the gray matter of the disease, the gray matter part of the disease. My question is, why usually it's the case that people think that, or maybe it's true, I don't know, that with disease, this kind of analysis is not, because you mentioned something related to tumor, totally agree with you.
Mm-hmm.
The point is that when the disease is more subtle, like it's not affecting directly the gray matter. Like the tumor may change the shape in the surface of the gray matter, but with multiple sclerosis, it's more of a matter of indirect effect. So it shrinks the amount of gray matter. So do you think that it's useful to use these kind of methods?
Yeah, good point. I think right behind you as well, there's an expert on lesions as well. And but yeah, it's basically if you lesions mostly arise all across the brain, so it's volumetric versus surfaces. It's mostly surfacic work. But still, if you want to play around with the thickness of your gray matter, the thin outer layer of your brain, gray is outside, white is inside. Those are because if think of this framework, I'd call it a framework to analyze data on a surface or data on a manifold in high dimension. But in 3D, you have this brain surface, and then you have data that lives on the surface, which is a thickness. Every point on your brain has a thickness, the gray matter, the outer layer that you have here. And if you want to analyze, okay, different areas, maybe there's some portions that in the population size, population-based, there's something that becomes a bit abnormal, but you want to learn basically data that lives on the surface. And the data, what you're mentioning here, is a thickness of the brain. And what you're telling is, depending on where the lesions are placed, well, this would affect this data, the surface thickness, on the surface. So you have the tools to learn. I never explored this approach though, but I didn't go into the details, but to learn here, there's a few things that is more or less classical, you probably know as well, but it's in the brain, you have the thickness of the cortical thickness, the gray matter. The curvature as well is another thing. There's a bunch of metrics, but those are fundamentally data that lives on the outer surface. So then it becomes a nice tool framework to play around with this. That could be a nice, I never explored this, in fact. Yeah, lesions. So I'm not an expert on lesions. Probably Tal could mention a bit more, but depending on the lesions, if it affects the thickness, that could be really fun to play around with this. I don't know what you think, Tal. Okay. Yeah, I'm sure. Yeah. Mm-hmm. Okay. I don't know what you think, Tal. No, you have the microphone, in fact.
Yeah. Well, I think that we'd have to think about that a little bit carefully, but it requires a bit more thought. But I do have a related question. So first, I want to say thank you so much for this talk. It was an excellent talk, and I love to see the evolution of this work over time. It's really beautiful work. So thank you. So just a quick question, because what you mentioned, comparing different brains, let's say, or things like that. So you mentioned under limitations that it has to have the same topology, and certainly at some scale, all brains have very similar topology. But when we're referring to specific cortical folds or things like that, I was just wondering if you could comment in terms of whether that is a limitation, and is it just a limitation at some scales, or what your thoughts are?
Yeah, it should be even in the limitation as well. But what I'm describing here, the spectral vibrations and so on, it vibrates fundamentally, to me in my head, it's at least you vibrate a geometry, but then you're tied with computer tools or mathematical modeling, which is the graph in that particular case. But the brain, if you have a super fine, refined graph, that's almost as close as the real surface, that's okay. But as soon as you start to have a different scale, different resolution of your graph, so those are about 300,000 nodes, graphs of 300,000 nodes. That's more or less the scale that you have here. But if you break it down or coarse it down to all the way to, I don't know, 3 nodes, very extreme, no? But it's, at some point you start to break the geometry. And as soon as you start to break the geometry, things starts to get weird. But as long as you're coarsen the graph, as long as the geometry is preserved, as long as you see the folding, those should describe the same geometry. So it should vibrate, or the colors that you see here should be more or less the same type of vibration. So depending on how coarse you want to go, until you destroy your geometry, this should be good in that case. But as soon as you start to destroy your geometry all the way to 3 points, for example, you shouldn't use those approaches. No, yeah, 3 is an extreme, but that's some 300,000 all the way to, I forgot, even 20,000. You still see the geometry, but way below, it's you completely destroy. You're not comparing the same geometry. You're comparing something highly folded to something smooth.
So the problem, just to clarify, the problem of sort of many to one or one to many of specific folds, like let's say, is that?
The many to one is different. Yeah, it's so yeah, the many to one is I call this more an interpolation issue where you have when you coarsen two nodes may become into one node. I didn't mention here, but in our work or Kartik's work as well, it's you rely on interpolation. You fall between 2 points, 2 nodes. So you have to interpolate values or things like that. You need to rely on the interpolation in that sense.
Okay, yeah. So
You
it's
triangulate, basically.
It's not inherently ill-posed, or
Huh?
is it inherently ill-posed? The problem of like this fold.
Yeah, so then you need to rely on interpolation in that case, because 2 to 1, when the real point is 2 points should be 2 points on the other one. So but just in a graph-based 2 nodes becomes 1 node. You were ill. It's
Okay, thank you.
Thanks for the nice talk, Hervé.
Mhm.
So you started this out, right, saying that if you have this regular grid on like just like a voxel grid or an image, you might not need this machinery, and then it's motivated by doing something on surfaces, which is awesome. But I was just wondering, is it known, like if you would use what you have now and you apply it, let's say, to a regular 2D image, you make a torus out of it if you want to. What's the gap? Like if you use this for segmentation, are you leaving a lot of them on the table, or is this method going to give me something that I would have just thrown it at a regular unit, for example? Is this known?
Good question. I guess probably a bit related to the scale, no? If as soon as you have or a very star-shaped, no? As soon as you have like highly folded, a star multiple spikes, for example, as soon as you have very high resolution, it's a matter of resolution as well. No? But as long as you have something very simple, a torus or something very smooth, just to CNN based is fine. No? But as long as you have something that breaks the related to longer range as well, no? Because the CNN, it all depends on the size of your convolution. But if you ignore that you're on a geometry, yeah, good points.
I mean, it's not a correspondence question, right? This is really just using the image and just pretending it would be irregular, even though it's not. Slap a regular grid on it. What would happen? And if there would be, if it would work super well for segmentation, I guess one could imagine just having like a coherent theory that you would always do it like this, right? You don't need to pick and choose. It's sort of like just a special case. Maybe.
Yeah, I'd say resolution or longer range. No, depending on if you have 2 points, but if the resolution of the geometry is like those super high folding of the brain, no, it's if you need more than a range of small neighborhood, the fold goes all around. I'm not sure I'm answering exactly the same thing.
I'm not sure if I'm answering. If I'm asking a proper question. My mind is just like you basically just do. Instead of a standard unit or whatever you want to throw at it, you just do it with a Fourier basis. Right?
Exactly.
Because essentially what you're doing. Like how much are you losing there, or is it sort of like qualitatively going to be the same thing? If you just want to, let's say, segment a natural image, right? There's no folding, nothing. It's just like a complicated signal on like a super flat space.
Okay. I see. On then I think it's mostly fundamentally, no, you're working on something extrinsic on an image. I'm thinking of MNIST, for example. You have different shapes of a 7 or a 2 or things like that. But if you have the extrinsic way to represent your image, Euclidean, and then you move it to Fourier space, then it's you're directly learning something that it lives on the digit, and so basically what you
I think probably should just drop my question.
Okay.
but it's more if you do exactly what you're doing, right? Then you have if your UV coordinates will just be the standard Euclidean coordinates, but you can still use the same machinery, right? You do your convolutions will just be done in the spectral domain. You can do your pooling. You do this, you stack this up, and then you use it for segmentation on the image. So this is a special case, right? It's just like the super simplified version of it.
Yes. Yeah. In that case, in that sense, yeah.
Omar, you can ask.
Yes, I had a question. Thank you for the interesting talk. So I had a question about this pooling on the graph. And you
Uh-huh.
mentioned that regularization term that helps learning based on the Laplacian. So I was curious if you could explain a bit more what this regularization is based on. I sort of missed it.
Where's this?
Yes, here.
Here, yeah. Basically, the Laplacian, well, to regularize the Laplacian is kind of nice because when it directly gives you the regularization. And the Laplacian, just remembering the math, it's a combination of, you have an adjacency matrix to build your Laplacian matrix. And the adjacency, it's directly given by the graphs that you have here. So, for example, those here, it's a bit going to the details here, but it's you have values on different nodes. And you have the adjacency matrix that happens here. This comes from the graph here that you just built when you were pulling when you were building your pooling layer here. You built a new graph, so that means you have a new adjacency matrix. This adjacency matrix here becomes, just by definition, becomes the Laplacian that you have here. And this Laplacian enforces the regularization just because it's a Laplacian. But if you remove this term, work usually happens only on doing your regular cross entropy and so on, but by ignoring a bit the regularization of the structure, the neighborhood structure that you have. And by ignoring this, you have all the classical problems of it's tricky to train or a bit unstable. So by enforcing this, it just helps a bit the optimization process. But the Laplacian, to directly answer the question, the Laplacian comes from the graph that you just built here. I'm not sure if I answered it.
Yes. So in the diff-pool paper, they also introduce a regularization. I think is it similar or?
Yeah, same concept, because this, again, it comes from the graph that you have here. Yeah.
Okay.
Diff-pool,
Okay,
exactly. Yeah.
Any other question? Check on that.
Oh, we extended a bit.
All right, so let's thank Hervé again.
Thanks so much.